So we're looking at a problem that's a little complicated. Let's say you were going to the airport and the airport requires your luggage to have the sum of all of the dimensions of your luggage to be less than or equal to 51 inches. So that's to say, if you added the height, the width, and the length of your luggage, it should be 51 inches or less. Okay, they actually do this, I guess. So, what do we start with here? Let's see, 44, 50, 56. Okay, so 56 is greater than 51. Is your bag too big to carry on the plane? Yes. Okay, so suppose that you could magically decrease the dimensions of the height, the width, and the length of your luggage by the same amount in all directions. That's to say, you could choose a number of inches to remove from the depth, the width, and the length of your luggage so as to fit the criteria of 51 inches. Okay, I'm pretty certain there's no such suitcase. We won't worry about that right now. The important aspect of luggage, I would say, would be the volume. How much stuff can they hold? Volume is a cubic measurement. It includes the product of depth, width, and length, so that the units of volume are cubic. If we start with the initial dimensions of the luggage, the product of 24 inches, 20 inches, and 12 inches will give you the volume of the luggage, which would be 5,760 cubic inches. Now, we have to remove portions of the seam. What they're going to ask you to do is to sum these linear polynomials, 24 minus x, 20 minus x, and 12 minus x. And that will represent the seam of the bag. Okay, if you do that, you would get 56 minus 3x. This is an equivalent expression. They wrote it backwards. So if you graphed it, it would be a line. So to model the volume, you would have to take the product of the length, the width, and the depth. Okay, if you multiply these polynomials, you would end up with a cubic polynomial. This represents the volume of the luggage as a function of the change in dimension that you applied. You can see the function reaches 0. If you took 12 inches off of all the dimensions, your depth would be 0. And you would have a bag with 0 volume, which would not be a real thing. Wouldn't be a real... Okay, all that aside, let's look at this. This is a better graph of the same polynomial. What you'd find is that if you do the inequality of 56 minus 3x is less than 51, you'd come up with 1 2/3 inches. That's the minimum that has to be removed from the dimensions of the length, width, and height. So, the important part of the graph, of this cubic graph, is right here. This is the least amount that you could remove from the dimensions of your luggage and get it to the airport. or get it on the airplane. If we look at the volume there, let's see what the scale is here. It's going to be a little more than 4,200 cubic inches of volume. So here's a cubic polynomial. A neat thing about a cubic polynomial is if you multiply it by -1, it switches its end behavior, which we're going to learn about soon. Now for this one, the only meaningful part of the polynomial is in this region. This doesn't mean anything, and I mean according to our scenario, and you can't have a negative volume. There are plenty of problems where the negative range does mean something, but this isn't one of them. Okay, so they're going to ask you to compute the amount of the length, width, and height you'd have to remove, and then they want you to compute how much volume are you going to have when you do that. Okay, at the end of thinking about this, it's important to have some basic idea about the shape of a cubic polynomial. A cubic polynomial has, at most, two local minima or maxima. Alright, so here we see a dip down and here we see a dip up. This is one less than the degree of the polynomial, and that's a general finding. So we're going to go over that and other characteristics of polynomials next.